Welcome everyone and thank you for joining us today. The webinar will begin shortly and we'll discuss solar resource nowcasting. We still have about 30 seconds to wait, so we start exactly on time. And we're letting everybody log in. So we're also really pleased to announce that we have over 400 people registered for this webinar and from about 80 different countries. So we have people from the United States, from India, Brazil, China, Chile, Italy, Nigeria, from Saudi Arabia, and there's lots more countries listed here as well. So thank you so much for joining us. Okay, well, before we begin with the webinar presentations, I'm just going to give you a short overview about the International Solar Energy Society. So my name is Joanna Costello and I'm working at the ISES headquarters in Freiburg in Germany. And I'm just going to take you through our introduction presentation. So ISES stands for the International Solar Energy Society. It is a non-profit, UN-accredited membership organization. The ISES vision is to achieve 100% renewable energy for all, used efficiently and wisely. We represent a diverse membership of academics, researchers, energy practitioners, consultants, students, businesses, and advocates. ISES works together with like-minded organizations from countries around the world to advance the renewable energy transformation. By becoming a member of ISES, you are supporting the 100% renewable energy movement. So for more information, please see our website www.ises.org or our membership page join.ises.org. The presentations and recording of this webinar will be available for 24 hours on the ISES website. I've sent the link in the welcome message, and after that time we will post them to the members only area. So if you are an ISES member, log in and click on members area in the top level menu and you will already see the archive of past webinars. If you are not a member, visit our membership page and we encourage you to sign up. You are welcome and encouraged to ask questions at any time throughout this webinar. To ask a question, select the questions pane on your screen and type in your question. Please specify who your question is directed to so I can send it to that panelist. Questions will be addressed after all the presentations in a Q&A session. And we'd also like to encourage you to use the ISES discussion forum on LinkedIn to continue the Q&A and the discussion even after the webinar has ended. So I'll give you a little bit more information about our LinkedIn forum later on. Now I would like to introduce Dr. David Renné, the President of the International Solar Energy Society, who will moderate this webinar. So I hope you all enjoy the webinar, and Dave, the floor is now yours.
Well, thank you very much, Joanna, and hello to everybody out there. Today we're going to have three talks from three very outstanding researchers in the field of solar radiation resource assessment and forecasting. These researchers are key members of a task that's been organized under the International Energy Agency's Solar Heating and Cooling Program. It's called Task 46, Solar Resource Assessment and Forecasting. This is an international collaboration that's been going on for almost 10 years now, where a number of experts from around the world gather periodically to share information and to conduct collaborative research and reporting. So we have two very interesting topics that we're going to cover. The first topic will be on meteorological data for solar energy systems analysis, and then we're going to have two talks on the topic of solar resource nowcasting. So I'd first like to go to our first speaker, who is Dr. Kristian Pagh Nielsen from the Danish Technological University. He will be talking about meteorological data for solar energy systems. Dr. Nielsen has worked with meteorology, radiative transfer, and spectroscopy for more than 15 years. He received the Norwegian Doctor of Scientific degree in physics from the University of Bergen in 2005, and he now works as a meteorologist at the Danish Meteorological Institute, focusing on numerical weather prediction and solar resource assessment. And his title of his topic is Beyond Typical Meteorological Years, Meteorological Data for Solar Energy Systems Simulation. So Kristian, please, let's look forward to hearing your presentation.
Thank you very much, Dave. I hope everybody can hear me, and thank you, Joanna. So, my presentation is has taken basis in two projects, the IEA Solar Heating and Cooling task. Let's just maximize this window. There we go, that's better. The Solar Heating and Cooling Task 46, Solar Resource Assessment and Forecasting, and also in a smaller project that started just last year and is funded by Solar ISES, called the Beyond TMI project. And in this project, DMI, where I'm from, collaborates with the University of Oregon, the Solar Radiation Monitoring Lab, the CMAT, Min Paritech, SunTrace, and CSIRO. Well, in particular, these people work on it: Frank Vignola, Lourdes Ramirez, Philippe Blanc, Richard Meyer, Manuel Blanco. And for the IEA Solar Heating and Cooling Task 46, there are a lot of participants, but I'll mention my Danish colleagues from the Danish Technical University, Elsa Andersen, Janne Dragsted, and Simon Forbo, who have contributed material for this presentation. So I should mention the others are not responsible for this presentation, so if I say something wrong here, then it's my fault, and please correct me if you hear something. So why are meteorological data needed for solar energy system simulations? Well, basically, when you have larger plants, you need a large investment. So you need to go to the bank and take up a large loan. Also, it affects the overall power grid significantly. So you have to think about how to integrate it into the grid so that it works properly. For both these reasons, realistic simulations of the expected power output are required. So in order to do that for the future, you need a fairly long data set from the past. So at least 10-15 years are needed. It depends on who you ask whether you should have at least 10 years, or some people say you should have at least 15 years of data. And some base this on 30 years of data, as would be done for a typical meteorological climatology. For meteorologists, the most typical way to represent past data is climatological data. So that means you have monthly averages of the temperature, of the global irradiance, of the wind, and so forth, maximum and minimum values during the day. But they're not good for this purpose of solar energy simulations, because they do not contain the true variability and correspondences between the meteorological variables, because it's just averaged out. So that cannot be used in this context. So specifically, meteorological data can be used for solar district heatings, for buildings, architecture, so passive solar energy, for concentrated solar thermal electric energy plants, and for photovoltaic, and probably more things as well. In order to explain why we use the data that we use now, it's useful to look at the history of using them. So the first one to suggest using solar data for simulations were Benjamin and Cook from New Zealand. They made the so-called standard year, and they devised a method which has been used pretty much since then, where you select 12 typical solar months from a long-term data set. And they based this on the cumulative clearness index distribution. A clearness index, that simply you take the global irradiance at the surface and normalize it relative to what you have of irradiance at the top of the atmosphere. They also chose these months from the number of low pressure systems that were passing during the months, so you got a variability representative. The next type of data set that was made in the mid-70s, the reference year. And this is referred to as the Danish metrology. It's made by Andersen, Lund, scientists at DTU, and other Danish institutions. And it includes, unlike the Benjamin and Cook, not only solar irradiances, it includes 20 different metrological parameters. And they base their selection of the 12 monthly data on the averages and standard deviations of global horizontal irradiance, DHI, 2-meter temperature, and daily temperature maxima. So this was used mainly for solar heating and for buildings, and that's why they chose the months in this way. Then came the metrological year, which is the main data set used in the US and also many other places of the world, by Hall et al. Or Hall et al. 1978, and like the other methods, they also suggest 12 typical metrological months, and they base it on cumulative distribution of several weighted metrological variables. And it's more specifically defined with weight for each of these, so that it's always made in the same way. Just to illustrate what is meant by 12 typical months, I think it's useful to list an example. So if we have a 15-year data set of data from 2001 to 2015, the 12 months we selected could look like this. So basically you have 1st January 2001, then February 2014, and so forth. So you basically stitch together 12 completely different months and make one typical year of the typical months. So we don't see the stitches for the solar energy, the solar resource, because they are at night. But for the other metrological parameters, it's not so nice. You can do some smoothing over a few days here. But it is a bit of a Frankenstein's monster, I've heard people refer it to. So a main issue here is, of course, that all the untypical months are excluded. And they are actually interesting when you want to do simulation of your solar energy system, because they will happen in the real world. You'll not only get typical months in the future, so you are missing out on those when you use this type of data set. And of course, historical reasons for doing it this way are many. There is computational resources. It's easier just to have one year of data set than a very large amount. It's difficult to handle in the 70s and 80s. And also, when you have ground-based irradiance measurements, you'll have a lot of data gaps. So you may not have all the months with good data. So then by picking out these months, or a subset of months, you can then avoid that problem. So these data sets are still used for applications today. So reference years have developed in IEC Solar Heating and Cooling Task 9. Skartveit et al. Lund made the design reference year, which is a development of the original reference year. There's also something called the test reference year. And they include also 5-minute resolution direct horizontal irradiance and global horizontal irradiance. And not too many years ago, there's also an ISO standard made based on the reference year, the energy reference year, ISO 15927. So the typical metrological years has been developed into TMY2, TMY3. So gridded data sets have also been made where you use satellite data to make a gridded data set that then can cover a large area. The TMY weights are defined in this table here. I have a link to it here. I hope it works for you if you want to know the details about that. In recent years, we have had the project, the FP7 project in DORS, where satellite-derived TMYs are also looked into. So of course, The best data you can get is a ground-based station that's properly maintained and properly calibrated, but for many places you'll simply not have a long enough time series to do that, and you'll not have the full geographical coverage. So therefore, using satellite data, you have the advantages. So many of the more recent data sets are based on satellite data to a large extent. So they define a driver. This is a one-dimensional composite time series from the multidimensional meteorological long-term data set, more related to the energy production of the solar energy conversion system of interest. And what that means is that depending on which type of energy you're interested in, you should weight which type of meteorological data are typical in a month differently. And the point is, you cannot get a month where you have all the meteorological data typically at once, so you have to choose. So for instance, if you have concentrated photovoltaic or concentrated solar power, direct normal irradiance is by far the most important parameter, whereas temperature and global horizontal irradiance is more important for the solar heating. Another recent development that is ongoing is an IEC standard that's being made for generating a representative solar year. This originally started as a Spanish initiative who realized that many people were using yearly data sets for solar thermal electric simulations in many different ways, and there wasn't any standard for doing so. And then they combined the original TMY and reference year methods with a method that's based on the direct normal irradiance, which is important for the concentrated solar, and are now finalizing, I believe, this standard. They also include methods for doing proper gap filling, and combining data sets. NREL, solar GIS, people make products. Recently there's also been some concern about overall research trends due to dimming and brightening. So in many places of the world we see significant trends in the global horizontal irradiance resource. This is presumably due to changes in pollution. So in areas where you get more and more pollution, you get less and less solar resources. And in areas like Northern America and Europe, where we've gotten less pollution during the last 30 years, we see brightening. And of course that makes an issue. If you use a 30-year data set from the past to make your meteorological data sets, then this will have less of resource if you had brightening during this period than what you currently have. So some people have said that then you should use shorter data set, perhaps only 10 years. But this is an ongoing discussion. Instead of using just these typical years, you can do multi-year analysis. And this is an example that DTU have made in Dragsted of multi-year analysis of solar collector performance. And here you see for 4 different sites, and this is then run for 4 different solar collector fluid temperatures. And you see then on the y-axis the yearly thermal performance in kilowatt hours per square meters. It's a few, the letters are a bit small, sorry about that. And you also see on the very right hand side in each of these 4 sub-panels the old design reference here. And you see for most of these sites the resource is clearly less than it has been during this first decade of the 21st century. Here's another example of multi-year analysis. This is also compared to a reference here. This is from Nuuk, the biggest city in Greenland, from the 1990s. And here you in fact see that the reference year has higher, if you use this data set, you get a higher yearly thermal performance than for the other years. And this is then actually because somebody who made this reference here made it to be a wind reference here with representative wind data. And that's of course then a big risk if somebody is making the reference here for something completely different, not even for any solar application. You can get a data set that's completely unrepresentative. So that's something to be very aware of. Who made this and how did they design this data set if you use it? The yearly variability is of great interest because you want to know how much does it vary from year to year and how much resource will we get in a bad year. And many people are interested in getting the P90. The P90 is the percentile above which 90% of all years will give more irradiance or energy production. It's often described as energy production. And this is often based on the assumption that the data are Gaussian. Here's an example where they are clearly not Gaussian. So that's something to look out for as well. So the Gaussian distribution is the black curve. You see it doesn't follow the data. In this data series of 43 years, some volcanic years are included. So you have Pinatubo and some other powerful volcanoes in the 1980s, and they then give these very low values that sort of fall outside. So if you remove them, you can however still see that the distribution is a bit skewed. This could be because that when you have a site that gets a lot of sunshine, you will never get more data than the clear sky year. So then you will not get the symmetrical distribution. In many other sites you will have something that's much more normally distributed, but it's something that should be tested. Volcanic eruptions of this magnitude happen quite rarely. So you can see during the last 150 years we only have a number such as what is shown here. So maybe 9, 10 big eruptions. What happens is when you have these major volcanic eruptions, you get sulfate in the stratosphere, and this can stay up there for several years before it falls out. And these sulfate droplets, they scatter away the sunlight and then reduce the overall resource, and particularly for the direct normal irradiance. Recent data of ice cores shows that this can be simulated. You have data with 2,500 years of data of sulfates from ice cores, where you can then get an idea about how powerful are they and how often do they occur. One problem with these ice cores is, for instance, the ice cores from Greenland. You will get sulfate from local volcanoes that does not come from the stratosphere, for instance from Iceland. But in the future, more isotopic analysis will be made of these data to separate sulfate from the stratosphere from the troposphere, and also to recognize which volcano the material comes from. You can actually do that today. So within a few years we should be able to assess also the risk of volcanoes. So uncertainty in the measurements or satellite data, derived data, must be documented and accounted for. And this is also important when you look at the statistical distribution, that you don't just have the natural variability, you also have an inherent uncertainty in the measurements. And you also have an uncertainty in the statistical sampling from the number of years you have relative to what your real distribution is. Whiting et al. Have written a nice paper about this. Separate analysis of volcanic years, so in the typical meteorological years, for instance, these are not included so that they don't affect those. And that's worth keeping in mind. And then you should test just the non-volcanic data have a Gaussian distribution. And you could also look into whether adjacent years are correlated, which they can be. So Philippe Blanc here suggested you could use the Hurst coefficient to analyze this, which is interesting. So future trends we cannot forecast, so we don't know how much people will pollute in the future, and climate change effects on the global irradiance resources also difficult to say. But scenario analysis can be made, for instance, using the IPCC scenario data of aerosols. I don't know how much time I have, Joanna.
Yeah,
okay, I'm good on time.
You're fine. Yeah, keep going.
Okay, good. So in north of Copenhagen at DTU, we've been looking into the directional variability of the solar resource as well. So we made a setup like this on a platform of the roof of the institute. where we have 16 parameters that are covered with domes, where each dome has an opening that's either 1/8 of the sky in an azimuthal direction or 1/16 of the upper sky. And using this and measuring with the 1-minute time resolution, we can then also get an idea about the variability of the diffuse directional irradiances, because a lot of the diffuse irradiance is in a specific direction. So in Denmark we are far up north, so we are interested in utilizing this for lighting of buildings and also for passive solar heating of the buildings. So we've done some empirical analysis, and this has mainly been done by Niels Andersen, I should mention. And here you see if you have the solar azimuth within plus minus 15 degrees relative to the opening of the dome, you get this diffuse fraction as a function of the clear sky index. And the clear sky index, that is then normalized relative to the irradiance you'd get at the surface during clear sky conditions. We use a clear sky model to simulate this. Here specifically it's the Xavier model from 1990. And what you see is that when you have 1 in the clear sky index, you have perfect blue skies, you get the least diffuse irradiance. And then when you go down in the clear sky index, you get more and more until you get a maximum. So here you see the effect of the circumsolar irradiance, which is then beyond the 2.5 degrees half angle that's commonly defined as direct irradiance. Then when it gets even thicker clouds, you go down towards 1/8 of the irradiance, because we're looking at a 1/8 opening. We also have the effect that when you have a higher clear sky index than 1, this is typically because you have over irradiance, that you have clouds that are distributed in a way where you get locally and temporally more irradiance, and then you get an increase in this diffuse fraction as well. When we step to the azimuthal direction from 30 degrees to 60 degrees, we also see an effect of this circumsolar irradiance increasing with a maximum at around 0.5 of the clear sky index. Another thing that's interesting here is this seems to be fairly independent of the direction of the opening. So you see you have here the points from all 8 cardinal directions. It's not exactly north, east, northwest, it's a little besides that, but you see there's not much difference between those. Spectral variability is of course essential to know for photovoltaic systems, so that's not included in many datasets available, if any, but it can be simulated with a fairly low amount of input arguments. You have models that can do this. You have, for instance, the Libratron Desort model. There's also the Libratron Mystic model that can do 3D simulations. These are quite heavy models that do a full solution of the radiative transfer problem. Libratron is made by a German group together with a Norwegian group, and has been developed for many years. It's a very nice library that also has a lot of data sets to use. But it's for people who know what they're doing to run. It's quite complex. You also have the SMARTS model, which is then a more efficient way of calculating spectra than Desort, for instance, made by Kristian. You can get that from the NREL webpage. But again, it's for experts. If you don't know about atmospheric optics and all the complexities of this, you shouldn't use it, and rather get in touch with an expert who can run these things. So here I'm just showing how the spectrum changes for changing cloud water load. So you have the upper curve is the top of the atmosphere spectrum of the sun, and then you have a curve showing the blue sky spectrum of diffuse irradiance and the direct beam spectrum. You have some cuts down into this, which is the water vapor absorption band. Here you have the CO2 absorption band, and you have ozone absorption bands, and so forth. Helium as well, of course, in the solar atmosphere. So when I increase this, you get more and more diffuse irradiance until all of the irradiance is diffuse, and you see also that the spectrum is changing so that the infrared wavelengths are disappearing. So this means you get relatively more energy for your PV system or for illuminance, that is natural light, compared to the reduction in the total global horizontal irradiance. So, well, now I'm almost done. A future prospect which we have been looking into in the Beyond TMY group, and particularly Manuel Blanco, who's also co-author on this paper here, is generation of realistic multi-year data. So if you know how to describe the data statistically, you can then make artificial data for a large period, which also then can be used to sample uncertainties, statistical uncertainties. And a paper was published about this last year in Solar Energy. Very interesting paper, and this is, we believe this is something that's a very good future prospect for meteorological data. I think also artificial data has been looked into by the company Metronom before. So, concluding remarks. Yearly meteorological data sets should be chosen with care, as they can be optimized for different technologies. So they may have been made for a technology which is not the one you're trying to use them for. But you don't really see that from these names. If multi-year meteorological data are available, these should be used instead. And in many cases you'll use satellite-derived data. Then it's important to use data that has been properly site-adapted. There was a previous ISES webinar, I think last year, where there was a very nice explanation of site adaptation by experts in this. And this should be done with at least 1 year of ground-based data of high quality. And finally, data uncertainty must be documented and should be based on blind testing. Okay, thank you.
Thank you very much, Kristian, for your very interesting presentation. Just a reminder to our many participants out there who are have joined this webinar, please, if you have any questions for any of the presenters, please enter them into the questions area of your website. So now our second speaker, now we're going to move into the topic more specifically of solar nowcasting. And our next speaker is Professor Jan Kleissl from the University of California at San Diego. Dr. Kleissl researches the interaction of weather with engineering systems, in particular building energy use and solar power systems. He's an expert on solar resource assessment and forecasting and is co-director of the University of California San Diego Center for Energy Research, and is also chair of the American Solar Energy Society Resource Applications Division. Dr. Kleissl's solar variability models, sky imager solar forecasting tools, and numerical weather prediction solar forecasts have been commercialized and are being used operationally to advance solar power integration. He received his undergraduate engineering degree from the University of Stuttgart in Germany and a PhD from the Johns Hopkins University, both in environmental engineering. And I should also point out that Dr. Kleissl is also one of 4 subject area editors of the International Solar Energy Society's Solar Energy Journal, the official journal of the Society. So Dr. Kleissl, we're very pleased to have you here. Your talk was titled Sky Imager Solar Forecasting for Distribution System Operation.
Yes, thank you, Dave. Yeah, I will show today a nice intersection between the solar resource forecasting and how we use that data in making engineering decisions and making our engineering systems work better. I'm focusing on the distribution system. That is a set of power lines that's generally running at a lower voltage, and that's taking the transmission power and feeding it to the homes. And the link between those transmission and distribution systems is the substation, which is typically something you find in your neighborhood. It's a plot of land with a lot of wires and a lot of electrical equipment, big fence around it. So we're looking at the lines from there towards your home. And here I'm showing one example of a distribution feeder in San Diego. This work was done together with my graduate students who are listed on the right. Let's move right in. So quick background, which should be no news to most of you, that PV has grown substantially. Just in the United States, we added 2 gigawatts of PV on distribution lines in 2015, which is 66% higher than the year before. And that in some countries, that large growth caused some bottlenecks in how these systems are accepted into the power system, so that either technical issues of suspensions or also restructuring of incentive programs that are trying to slow this growth. But we think that we can leverage more potential for improving the utilization and the control of these solar power systems that would more easily allow large quantities to be on the grid. Just a very brief background on how the power system responds to solar irradiance variations. You see on the left-hand side a base case without solar, and the right-hand side is a case with solar power. And we're going from the left to right. The left is a substation. That's where you have your transformer from the transmission system going down to the distribution system. And then as you go towards the right, you're having the customers connecting and drawing power. And the voltage is the critical component here. If you, in the United States, the voltage is required to be within 5% of what we call 1 per unit, which is basically the nominal voltage, whatever it may be in a given distribution line. Other countries it may be slightly different, and certainly in some developing countries these voltages may fluctuate by much more than that. But these are our standards, and utility is required to maintain that range of voltage. So in the base case, we see if we have high load, that means we get drawing a lot of power, then the voltage drops quickly. And so in the middle of the feeder we have here a transformer at the distribution system that will step up the voltage, and then it will make it such that the entire line from A to D is within the range. If we have minimum load, then the voltage drop is smaller, and we're staying more towards the higher end of the voltage band. Now when we add PV, and we add enough so that we actually get a backfeed of power, so you're exporting to the grid, you're consuming more than what you produce, you're producing more than what you consume, then actually the slope of the voltage curve changes, and we're now increasing the voltage towards the PV system. And in the max load case, that's actually a good thing, because we're not dropping the voltage towards the low end, but we're keeping it higher. But in the minimum load case, the second graph, there we see it's can be a bad thing, where now we're actually increasing the voltage to be out of band here. And that means that this transformer here that had before stepped up the voltage now would have to change its windings to step down or not do anything, and then we are back within the range. So my talk today will actually be mostly about these transformers. So I'll be studying how often and how much these transformers have to step up and down as the solar power is changing. That's really the key word here, changing. If we just had the people consuming load, that's a fairly smooth signal, so you don't need much adjustments during the day. But if you had a lot of PV and clouds moving in and out of the feeder, which is not a very large area, typically about on the order of 10 to 100 square kilometers, then actually these voltages will jump around a lot more, and these regulators have to work harder to keep the voltage within these bounds. So that's motivation. Now I want to show you our data input. Then we're looking at actually power simulations of the distribution system, and then study the impacts of high PV penetration. Finally, then look at how can we mitigate some of these impacts if we use solar forecasting or nowcasting. So this is background on our sky imager system, something we built in-house that we have also deployed for others. So if you're interested in obtaining one, we sell these at cost to others who are doing resource assessment or forecasting. And it's a high-quality camera system that takes an image of the sky with a fisheye lens. Then you use the red-blue ratio, which is a spectral method, to obtain the map to the right, which is the cloud decision map. This shows what is cloudy and what is clear. And then we basically have to overlay these clouds onto the ground. So we see here a snapshot of about 2.5 by 4 kilometer area of the ground, which could be a distribution feeder. We're now overlaying these clouds on this map here at the same time as showing the solar power systems on that feeder. So with those systems you can forecast typically about 10 to 15 minutes ahead, depending on height and the cloud speed. So it's a fairly limited horizon that doesn't help much with most energy markets, but if we show it in this example, actually it can help with the distribution system operation. So in this slide you see how we overlay these cloud maps on a distribution feeder. And what's now critical innovation here is that we actually can now specify for each PV system that we map out on that feeder, specify its own irradiance profile. Typically we don't get solar power output at a very high resolution from solar power systems because they're all owned by different parties and they don't share the data. But if you just have one sky measure system in this area, we can actually then generate these solar power input time series for all of these different systems. And that way we can better replicate what actually the spatial or geographic smoothing is of the total power output compared to a single system. And so here's an example of how that smoothing works. So on the left-hand side you see the output from 3 different systems. They're randomly picked from the distribution feeder, and we see the irradiance profile from these systems, and we see a clear period between 1 and 2 o'clock here, and then some partly cloudy conditions. If we average those 3 systems together, we see we're already generating a much smoother signal. And then if you look at the power output from all these systems together, then we see even more smoother signal, where the red line here is the output from all the systems together. And it's here negative because we're feeding power back towards the substation. So this method can simulate well this impact of geographic diversity of the different solar power systems, and we'll see later that that is important to get a more accurate estimate of the impacts. So looking at our simulations, we are simulating 5 feeders here, which are from California. The black lines are the power lines, the colored symbols are the locations of the PV systems, and the color is proportional to the size of the system. So we see on the right-hand side an urban feeder that's pretty small, just a couple of kilometers. Left-hand side is a more rural feeder where we have over 10-15 kilometers in length. And the voltage drop will be always larger on these longer feeders, given the same power line. Now here's an example of an animation that actually shows the voltage. So remember, we want to be between 0.95 and 1.805. On the top is the time clock counter. You can see at nighttime it was a pretty smooth operation, but now in the daytime we see how the voltage jumps up and down a lot. This is an extreme case, so we're having a lot of solar on this feeder, and that's actually not happening in practice, but it gives you some indication of how really the voltage fluctuate if you have a lot of solar power. And then now back at nighttime you see everything is nicely smooth and under control. So clearly solar power systems do have an important impact on these voltages on the feeder. It's however highly feeder dependent, so as we will see, some feeders actually have even at very high solar power levels have almost no impacts. So now we'll first look at one parameter that's maybe the most accessible parameter to most engineers, and that is the line losses. So these are associated with the power going through the power line. You have a current flowing there, and then the resistance of the power line will cause there to be a loss, and the power lines heat up because of that. So we see here on the x-axis the PV penetration level. That's defined as the amount of solar power capacity over the feeder rated capacity. So 100% penetration, we basically be producing as much solar power as this feeder is rated for. And then the line losses are normalized so that if you had no solar power, then we would be at 100% line loss. And we see that as we add solar power, actually we're reducing the line losses. That's because the power is produced locally and is consumed either at the house itself or at the neighboring houses, so it has a very short distance to flow. But as we go to higher and higher penetration levels, then actually we're reverting this trend, and we actually increase the losses, because now a lot of power in daytime is actually flowing from the different power systems all the way back to the substation, because it's too much to be locally used on this feeder. So here now is a graph of these tap operations. So remember, these were the transformers on the distribution feeder that try to regulate the voltage, and they operate a tap, so they move a large set of windings away and to the transformer. In that way, they change how the voltage steps from upstream and downstream of the transformer. These are very expensive pieces of equipment. These are mechanically operated, so there's a wear and tear on these systems. So we really want to avoid a large number of tap operations. Now we're seeing here these 5 feeders, and let's first just look at the colors. We see that some feeders, like feeder B, has actually less than 0.1 tap operations per day, which means that only every 10 days on average you actually have even 1 tap operations. These are the urban feeders that are more clustered and it's much easier to control. Then on the other extreme we have feeder A, which is a rural feeder. It's very long and it has a PV system near the end of the feeder, so it's really the worst case you can imagine. And in this case we now have hundreds of tap operations already at 0% PV penetration, and then we go to higher penetration levels. We actually go exceeding or approaching 1,000 operations per day. So this would be a significant concern for the lifetime of this equipment, and that would be basically integration costs of solar power associated with replacing these taps and transformers on a more frequent basis. And now let's focus on the dash versus the solid lines. And so keep in mind this is a log scale here, so this distance here looks pretty small, but actually it is several hundred operations for this feeder A here. And that basically shows you if we used what is currently being done, which is you just take a single irradiance sensor or solar power system and you apply that same profile to all the different systems on the feeder, then you can have a very large variations here. But then the other extreme is that you use what our sky emitter does, and then we excuse me one second. And that sky emitter produces a different solar power profile for each system on the feeder, and that basically simulates the geographic diversity that we can get. We see that there's a fairly major impact. Really, on some feeders we get 70% change in the amount of tap operations if you use the sky emitter approach, which is the real approach, expected to be the closest to the real data. So that's partly good news, partly bad news. So some feeders have very low, almost no impact with solar power. Some have very substantial impact. But now, what can we do about that? And I will show you some tools out there that we can utilize to really reduce these impacts, and what I will not cover today, even reverse the impacts, and that will help the utility companies and the solar power industry to keep growing. So one approach is the forecasting, and we see here we can basically design some very simple rules for if we know the future state of the distribution system, is it actually recommended or necessary to even change the transformer tap, given this future knowledge. And so the first example here is rule 1, where we currently here are at the end of the red line. We are looking ahead now 5 minutes in the future. Forecast, you feed that through our distribution system simulation model, and then we can generate the dashed line, which is the expected tap position at each one of these time steps. Now we see the tap is jumping around here. It's going up, then down again, then up again, and we can say, well, this process is not very efficient. It's just following the solar power production up and down, but there's a delay in operating this tap, which is can be up to half a minute or so, and so we're really sort of hunting this curve. And it may be more efficient to actually, in this case, do nothing, because we'll just stay here with the black dash, stay the same position, because we know in 1 minute actually we would be back there anyways. we're avoiding a operation in this case here. The case is where it's not going back and forth around the point where we are currently. It's moving in one direction. So here at the end of the red line, we see the tap is position is higher for all of the future 5 minutes, and so we know we should really step up, but we don't want to step up all the way because again it's coming back down in just 1 minute, and so we're stepping basically to the lowest predicted position in the next 5 minutes, and again we're saving a lot of tap operations. Yeah, so let's see how this works in practice. So we should see here one example from this one feeder that had a lot of operations, and I should disclose here that this method really only works if you have a lot of operations, because if there are operations in the next 5 minutes, then there would be no benefit from this method. But here there is a large benefit. We're starting with the blue dash line. The tap is jumping up and down as the solar power output changes. Then if you use different forecasts, an actual forecast for the sky imager or a perfect forecast, assuming perfect knowledge, then we can go to 46 or 15 tap operations, so a major reduction, 90%, almost 90% in this period. So if you look at a larger time period, 90 days that we simulated, looking at different transformers, we see number one that if there are transformers that have very little tap operations to start with, then it go from blue, which is the default baseline. These forecast cases, we have no change there. But for those transformers that have a lot of tap operations, we see a large reduction, so going from 70 to 80 operations per day down to 20 to 40 operations per day. What's also interesting here is that the forecast accuracy actually is not that important. As I'm sure the next speaker can acknowledge, forecast very difficult topic, and if you wanted to get a forecast for every single PV system, every given time step, it's actually very challenging. But here we go from our actual forecast, which is has a lot of error in it, almost no benefit in transformers, which means that it's really more important in this case to understand the amount of variability going forward than the exact output of each solar power system, because you're really just doing a very qualitative feedback control on this forecasted time series. And so this is good news for those who do forecasting. We can get away with less accuracy. Now, one more concern is if we manipulate these tap operations that really were designed to keep voltage in a tight band, could we actually have on the voltage quality, which means on not staying within that 5% band around the optimal voltage. And so here we compare basically the voltage histogram of these different methods of operating, and we see that we have the same histogram here for all three methods. However, if you zoom in, then you would see that actually we have a very few events, about a few minutes every day, where actually we do have a large voltage excursion happening because we did not operate that tap. And so we're currently working on techniques that that basically detect that the voltage is very high. We would actually then operate the tap, even though our recommended to remove that incidence, because we do want to maintain the required voltage. So we have shown that you need to consider the geographic diversity of solar power on distribution systems to realistically simulate what's going on in terms of the power quality impacts. And for that purpose, sky images are ideal because you can get highly resolved maps of cloud cover that are better than what you would get from a satellite, or certainly better from a numerical weather model. Then we see that there's a reduction in the voltage variability, so the tap operations, if we go from using the same irradiance input to every PV system versus using a sky imager map to have a unique input for each power system. So if we compare those two extremes of how we specify solar power output, then we see that there's up to a 7% increase in tap operations for these very high penetration levels. So it's important to correctly specify the solar resource, but it is highly dependent on feeder and penetration levels, so certainly nothing that we can generalize. It goes from 0% to 70%, and depends very much on the feeder configuration. And then, however, on those feeders where we do see these large number of tap operations, we have shown that the solar forecast can reduce the sub-operations, and we found up to 60% reduction at these high penetration cases. And they've also found that the forecast accuracy is not critical to achieve these reductions. So that's all for today. I just want to point out that something we did not consider here, and it will be a major impact in the future, is the inverter reactive power control. So you can actually use the solar power inverters to also control the voltage, which we in this case did not consider. But if you do that, then actually we could most likely turn the table around. And now, rather than talking about PV impacts and mitigating them, actually we would be having a PV benefit, where if crop you could reduce the number of tap operations because you control voltage with the PV inverters. So that's currently the works in California and also in the United States. I know Germany has already done that for a few years, and it's clearly the way to go, and it will have potential to actually generate extra revenue, reduce costs by having solar power on distribution systems. Thank you very much.
Thank you very much, Jan, for that very interesting presentation. I see we have a number of questions coming in. Just a reminder to all of our participants out there that if you have a question for any of the speakers, please enter them into the questions area on your website, and we will address the questions at the conclusion of the presentations. So our third speaker, also to talk about the topic of nowcasting, is Professor Philippe Blanc. He is the head of the research group involved in renewable energy resource assessment within the research center titled Observation Impacts Energy for Minas Paris Tech. He's working on the modeling of solar radiation and its assessment from in situ measurements and the satellite images. His background is related to signal and image processing, data analysis, and applied mathematics. And he's currently a leader of the subtask Advanced Solar Resource Modeling of the IEA Solar Heating and Cooling Task 46 Solar Resource Assessment and Forecasting. His webinar, by the way, I should also mention that Professor Blanc is also an associate editor working with Jan Kleissl on the solar radiation and energy meteorology area of the Solar Energy Journal. Professor Blanc's title of his webinar presentation is Nowcasting of High-Resolution DNI Maps Using Multiple Fisheye Cameras in Stereoscopic Mode. He's going to talk about some preliminary results of this under the European project called DNI-CAST. Professor Blanc.
Thank you, Dave. Hello, everyone. It's a pleasure for me to present some results about DNI-CAST. So first, a few words about the project DNI-CAST. It's a FP7 project involving 13 partners, and the coordination is done by the OME, Observatoire Méditerranée d'Énergie, and the technical coordination is done by the DLR, the German aerospace. So the aim of this project is to develop direct normal irradiance nowcasting methods. Nowcasting means that we want to achieve forecast from zero, for time horizon of zero, which means real time, up to few hours, to optimize operation of concentrating solar technology, which includes CSTE, concentrated solar thermal energy, and also CPV, concentrated photovoltaics. The main objectives of this project is to establish a portfolio of innovative methods of nowcasts for DNI, using different sources of information, going from the ground-based methods, the satellite-based methods, and the numerical weather prediction-based method. The aim is also to combine these methods considering the different time horizon, and to validate these methods and to assess the influence and the improvement of this DNI nowcast on the nowcasting of the power plants. The objective is also to involve the potential users of these nowcasting methods and to assure proper dissemination and exploitation of projects, activities, and results. So you have the website of this project here. So going for now for the nowcasting at a very short term, the objective here is to provide nowcasting of DNI maps, spatially resolved, with multiple fisheye cameras or all-sky images. The time horizon for the forecast is ranging from 0 for the real time to, let's say, 30 minutes. The temporal resolution of this time series of DNI maps is 1 minute, and the update period is 1 minute. The spatial resolution is 10 meters, and the spatial coverage is, for the forecast, 2 kilometers per 2 kilometers. Within the framework of this project, we have 2 years of experiments on the Plataforma Solar de Almería, in PSA, in the south of Spain, which is operated by the CEMAT, the Center for Energy, Environment and Technology of Spain, and also by the DLR, the German Aerospace. In this figure, you can see the PSA from Google Earth. This is more or less 2 kilometers per 2 kilometers. Here we can see the solar tower, 2 solar tower plants, and I have printed in this figure the 4 cameras, fisheye cameras, and the distance between these cameras. We will see that it will be very important for the stereoscopic mode. Is ranging between 500 meters to 900 meters. So first of all, some description about the fisheye camera that has been used for this project. It is a Mobotics Q24. It has been chosen by the DLR. It's a fully standard security cameras that is not dedicated especially for solar energy purpose. And it's cheap, less than 1,000 euros, robust and easy to use. So the DLR managed to do this acquisition setup every 30 seconds with 3 exposure times to have a large range of dynamic of the image. The angular resolution is between 0.1 and 0.15 degree, and we have a almost continuous acquisition since 2014. So first of all, before doing this nowcasting method, first of all we had to manage, Min Paratech managed the geometry calibration. This has been done with checkerboard, checkerboard pattern that has been acquired by the cameras, and taking these checkerboard patterns, we have applied intrinsic calibration using the Occam Calib, the free toolbox Occam Calib on MATLAB, to assess the focal, the optical deformation, the pixel centers, etc. of the camera. Then, looking at the comparison between the theoretical position of the sun and the one that has been detected on the images, we did extrinsic calibration, which means that we have assessed the 3D orientation of the camera to have the orientation of the camera, and then you have a complete geometric calibration. This is here a video looking at 1 day at PSA from 1 camera. Of course, it is accelerated, and you have from the beginning to sunrise to the sunset. I can redo it. So we can see a very complex cloud coverage, and we are working on this type of images to do this nowcasting. Of course, we are talking about using multiple cameras to do the stereoscopic mode. To understand that, in fact, we want to use the parallax between the images from two separated cameras with a base of approximately 600 meters. This is an example of the same at the same times from two cameras, so from two fisheye cameras with a distance of 600 meters, sorry. So you can see here, once one has been resampled, assuming a cloud-based eye of 400 meters, you can see here the parallax effect between the two images. Measuring this parallax effect as a type of term of image geometric disparity, we can have an assessment of the real cloud-based height of the cloud coverage on the real time. So I will now give you a brief description of the real-time methodology involved for the nowcasting. So for the moment, I consider the camera A as a master camera and the camera B a stereoscopic camera with a distance of 600 meters, but in the methodology you can have more than one camera as B. From the image A at the instant T, thanks to the work of the University of Patras in the DNA cast, we have applied the algorithm to do the cloud detection, so to detect in these images the clear sky pixel and the cloudy pixels, and in addition to have the cloud type, thin, thick cloud, and a classification of the type of the clouds, including the circumsolar area near the position of the sun at each time, in real time. Then, considering the two images, image A and image B, at the same instant T, we are doing a stereoscopic analysis by getting automatically typons on the image A, which means that we try to select cloudy pixel that has enough textural information to do the cross-correlation matching between this pixel in image A and the pixel in image B. Then we have these typons matched between A and B for different pixels corresponding to the clouds. And thanks to the geometric calibration, we are doing intersection of the line of sights and to assess for each of these pixels the cloud-based height. Thanks to this correlation and this intersection of the line of sights, we can also have a quality post-filtering of this matching based on the level of correlation and the minimum distance between the line of sights. So then, once we have sparse, pixels for which type matching has been done, for which we have the cloud-based height estimation, thanks to an automatic clustering, Chi-means, for example, based on the RGB image and in addition to the cloud-based height estimation, with a finite number of cloud layers, we can have an interpolation of each pixel of the cloud-based height. We have applied the same type of methodology, correlation-based techniques of the same typons, not between A and B, but between A and the same image from A for the previous instance, 30 seconds before. Thanks to this same type of correlation, we are assessing the cloud motion vector at each time, in a real time. Since we have, for all this cloudy pixel, the cloud-based eye and the cloud motion vector, we are assimilating this wind speed estimation from the cloud motion vector per layer. So we are averaging wind speed for each cloud layer that had been detected during the cloud-based eye estimation. Once we have the CMV and the CBH estimation, we can do a projection of these images, including all the information you can get from the images, for example, the cloud types, the cloud-based eye, etc., for the corresponding time of forecast, taking into account the cloud motion vector in a persistence way, and following the direction of the sunlight to cast the shadows on the ground. The relationship between the type of clouds projected on the grounds and the clear sky index that we are using for the nowcasting is based by the use of a real-time measurement of DNI in only one location on the site. So we need here for this nowcasting at least two cameras to do the stereoscopic modes, and also a real-time measurement of DNI to propagate the relationship between the clear sky index and the type of the cloud projected on the ground. Considering the CBH estimation compared to a celiometer, because on the PSA we have a celiometer on a very specific place. This is here for 1 day the images from the celiometer. This is the time here in the x-axis, and this is the cloud-based eye, and the spot you can get here is the detection of the cloud corresponding to each level of cloud-based eye. So if I superimpose the cloud-based eye estimated by the celiometer at the very end, the one that has been detected and estimated by the two cameras at the very vertical of this celiometer, you get these red dots. So you can see that there is a relationship between what has been estimated by the two cameras in stereoscopic mode and the celiometer. And if we do a comparison between the measured CBH and the estimated one from the stereoscopic cameras, you can get a nice correlogram with more or less 0.9 correlation and around 700 meters of error for this day, for the CBH estimation. This is an animation taking in one image, in one video, sorry, all the information you can get from the two cameras. Here you can see the sun, and you can see the cloud that has been detected. The patch corresponds to the CBH estimated, and you can also see the arrow for each patches, and you get here also the wind speed for the different layers that have been detected in real time. Okay, so using this type of information at real time, you can project, make a orthoscopic projection of the clouds, seen from the top, and this is a region between minus 15 kilometers to 15 kilometers, 30 kilometers as a spatial coverage, and you can see for one moment the clouds and their corresponding cloud-based height. This is here roughly the region of interest of 2 km per 2 km. Once you have this cloud height estimation at real time, you can get the shadow projection of these clouds, and you can notice that there are some artifacts here. You get some holes in the clouds because you have many layers of clouds, and of course when you have a lower cloud, it makes an occlusion of the higher clouds, and once you are doing the shadow cast, you get some holes on the ground because of these different layers. So now about a result of nowcast for 1 day, for a specific day. So we have made a nowcasting of the clearness index based on the shadow projected of the type of the clouds and a relationship between real-time measurements of DNI at one location, here at this location here. This is the meter, this is the region of interest. This is one place where we have DNI measurement, and also one of the cameras. This is the second place where we have the second camera, 500 meters away. And the result I present is assessed in this place, 400 meters away from this station. So this is the result for 1 day at a real time with a horizon of time of 0. So here you have in blue the measured DNI at this station, and in red you have the real-time estimation from the cameras. And you have here the statistics, very nice statistics, comparing the estimated one and the measured one. After, for the forecast of 15 minutes, here is the baseline forecast based on the clearness index persistence. You get here the results, and you can see clearly that this persistent forecast has a time lag corresponding to exactly the 15 minutes. So this is the baseline forecast, and we try to be better than this forecast. Using this nowcasting based on fisheye cameras, you get this type of, with a time horizon of 15 minutes, at the baseline station from the two remote places where are the cameras. You get some results. So you have some problem of missing clear instance, but you can see here that we have a nice estimation, a large amount of drops of DNI, but we can also see that we have some artifacts here, many artifacts due to cloud occlusions. We can do post-processing made here with a causal median filter, and we can get this type of results. Here we get very nice forecast, not so bad, sorry, because as said by Jan, the forecast is very difficult, especially if we want to predict the future. So it's not so bad, and you get here compared to the baseline forecasts a correlation of 0.63. You get a correlation of 0.76, but we have a large bias due to the causal median filter. So as a conclusion, we have presented here a real-time processing of fisheye cameras in stereoscopic modes every 30 seconds in real time, and the result has been averaged to 1 minute. This processing gives you information over a large spatial coverage of 30 km times 30 km typically, to do the cloud detection and classification, the cloud-based eye estimation, and the cloud motion vector estimation in real time. And thanks to this information at this spatial coverage, you can, on a very specific place, do the DNI nowcasting of DNI maps on the region of interest of 2 km per 2 km. And we are using one real-time perimeter measurements to do the relationship between images and ground measurements. So for us, it's very encouraging forecasting results. Of course, all the days are not the same, and some days are very complex in terms of, it's not only advection, cloud advection, you can have a cloud convection, and in that case, the CMV is not very efficient. But in some days, we have some nice results, but there is a need of improvements for example, for the post-processing, because we have, as we saw, cloud occlusion, so we have holes in the shadow on the ground, and therefore we have some error on the measurements, and the wind speed per cloud layer should be filtered by appropriate post-processing that should be done. The result I presented here is a result of a collaborative work from the German aerospace, who did the setup of the fisheye cameras for more than 2 years, and they will do the performance analysis of the DNI maps nowcasting with MeteoSuisse. University of Patras give us algorithm for the cloud mask and cloud classification, including in the circumsolar region, and we did photogrammetric algorithm for cloud-based eye and CMV estimation, geometric and radiometric calibration, and the nowcasting algorithm. We will present, we have submitted, to Solar Paces in Abu Dhabi, an in-depth performance analysis of this DNI maps nowcasting based on more than 6 months of images, June, July, and August for the winter, and September, October, and November for the winter season. And the performance analysis is based on the parameter and perimeter on the site. You can see here, perimeter in red and parameter in blue. And also, this is very innovative, 6 shadow cameras that are, in fact, cameras on the top of the solar tower, 87 meters high, looking at the ground and looking, therefore, at the cloud shadows, and therefore mixing the cloud shadows acquired in real time by these cameras and the perimetric measurement on the site, you can derive a reference DNI map in real time that should be compared to the one that has been nowcasted by the fisheye cameras. Thank you for your attention. this is the contacts of the projects from Inverter, Stefan Wilbert for the DLR, and Dr. Andreas Katzanditis for University of Patras. Thank you very much.
Thank you very much, Philippe, and thank you all for your participation. We have about 10 minutes to go through some of the questions that have been coming in, and please feel free to ask your question on the chat or on the question area of your website if you have questions for any of the three presenters. So the first question is addressed to the first speaker, Kristian Pagh Nielsen, and he asks, can you please explain the clear sky index? Is it global horizontal irradiance at the surface divided by the whole global horizontal irradiance clear sky? Is that correct?
Yes, that's exactly what it is. And we use the clear sky model of Xavier et al., which is the model that's also used in the Hirlam weather forecasting model. We made some slight modifications to it, but relative to the sort simulations, but otherwise that's what we used.
Okay, thank you. I think this question might also have been to you, Kristian. He thanks you very much for your presentation, and this question is, what is the difference between meteorological data and climatological data?
Climatological data classically is monthly averages. So if you look at a website from a major city like Vienna, you'd see that you have on it the climatology, where you have the average temperature in each month and the average wind speed and the average precipitation. So that's basically it. Meteorological data can be much higher resolution. 1 hourly resolution is used for many circumstances, but can also be 10 minutes or 1 minute.
Okay, thank you. This next question looks like it's to Professor Jan Kleissl. Jan, could you explain perhaps a little bit more what you mean by TAP operations?
Yes, the transformer in the distribution system is tasked with changing the voltages. It could be a voltage from a transmission level to a distribution level, which is a big drop, or it could be just a fine adjustment within the distribution system. And let's look at the latter case, where we sometimes would have no change in the voltage because we are well within our bound. But at other times, when there's a lot of solar power generation or a lack thereof, then there's a requirement for that transformer to adjust the voltage up or down. And that adjustment is done with the tap. And the tap basically means that we mechanically add or remove windings from this transformer. And then we go back to the basic physics, where we know the transformer voltage ratio is a function of the windings. And so you can basically add and subtract windings in a different amount of steps to achieve these voltage objectives, and that's what we call the tap change. So we're adding windings, we're changing the tap.
Okay, thank you, Jan. I don't see too many more questions coming in. We did have a general question about missing a citation on this Nowcasting summary slide. Just to remind all of the participants in this webinar that the presentations are available on the webinar section of the ISES website. Joanna can provide more details about that in a moment. And there is another question here related to this for both Jan as well as for Philippe, and that is the participant missed. He requested if there could be more links provided to the information on the topics that you discuss. There's a lot of technical information in the presentations, but of course we don't, because of limitation of time, we don't have the time to go into extensive detail. So there is this general question about how to get more links to some of the references referred to in the presentations. And I know that under the IEA Solar Heating and Cooling Task 46, there's a Task 46 website that has some general publications provided in it. So you can find that by Googling the Solar Heating and Cooling, International Energy Agency Solar Heating and Cooling Task 46 program. Does anybody, do any of the speakers have anything further to add regarding how to get more detailed information?
Yeah, for my part, you can also go to the Nowcasting project website, and you can download there some public reports, notably the full description of the algorithm involved in Nowcasting methods. And also, if we discuss with Joanna, I have a more complete presentation that I can upload for people who are interested.
Yeah, and for me, we just published the first part of the webinar in the Solar Energy Journal, and the second part that's currently under preparation for publication. I'm lucky that my name is quite unique. I think there's 10 people in the world with my last name, and only 2 of those have published. So if you just enter my last name in Google Scholar, you should be having an easy time finding those publications. But if not, please do email me, and I will send those to you.
For me, it's not the same. Philippe Blanc. There are many Philippe Blanc in the world.
Yes. Okay. Thank you. Here's a question. A few more questions as this come in. This one is to Kristian. What is the procedure to make TMY, TDY, TGY data? Which is the best among them? It's a big question. I don't know if you could come up with a quick response to that, or refer the person to further information.
Well, I could refer them to NREL, I think Aaron Hapter is working with this. I haven't worked with these because these are specific NREL products. TDY is a typical meteorological year where you only weight direct normal irradiances, as I've understood it, and TGY would then be a typical meteorological year where you only weight global horizontal irradiance. Whereas the TMY, the typical meteorological year, you would then weight a lot of meteorological variables like temperature and so forth. So that's the difference. So then it depends on what you're interested in. If you're interested in a broad meteorological data set, it should cover many things, or if you're only interested in a specific irradiance parameter.
Yeah, I think that's a correct answer. The NREL website has publications on TMY and also on, I believe, on TDY and TGY information. Also, one of the deliverables coming out of Task 46 is a best practices handbook on use of solar resource data. That link can be, you can find that link from the NREL website and also from the IEA Task 46 website. So there's further information provided there as well. Here's a question to Jan. You mentioned that Germany has been doing inverter control to regulate voltage. Can you give some more specifics about this?
Yes, not a lot, because I have not been intimately involved with that. But I would Google the German grid code. There's a public document that describes exactly what inverters can do and what they should do. From my understanding, the utility is in charge of controlling these inverters, and that the PV systems above a certain power rating, I think maybe 20 kilowatts, which is basically above what these small residential systems are, they are required to have this utility control and communications channel, and then they can then be set to do whatever the utility wants to achieve on the specific feeder. In many cases, you would use the inverter to move the voltage to a target set point. So if you want to have it at 1 per unit, then if you were below that voltage, you would add reactive power. If you're above it, you would consume reactive power, and that way it could be automatically nudged towards that voltage. In California, we actually just saw today that we also have published what is called the Rule 21 documents that also describe what the inverter can and has to do to comply with the grid code.
Okay, thank you, Jan. And I think we have time for one last question. This one is to Philippe. Can you please explain briefly the parallax effect? Philippe, you may be on mute. You may want to unmute your mic.
Sorry. Parallax effect, in fact, is the fact that you are looking something, for example, the clouds, from two different points of view. Just like you are looking things with your two eyes, you can get the depth estimation from the difference between what you can see from the left eye and the right eyes, and this is the parallax effect. So everything that don't have the same depth compared to the 2 points of view makes two different images, some geometry distortion, and this geometry distortion is called parallax.
Great. Well, thank you. I want to thank all of our speakers for their excellent presentations and for this very interesting webinar. And in closing now, I'd like to turn the microphone back over to Joanna for any final comments and wrap up.
Thank you, Dave. Yes, from me also, thank you so much to our excellent speakers for sharing their knowledge and expertise with us today. We had a very successful webinar with a lot of people online, so thank you so much to everyone who could take time out of their busy schedules today to join us, and we welcome you to join the next ISES webinar. They're held monthly, so please do keep checking our website and our emails for the next webinar. Well, that's all we have time for today. You can view the recording of this webinar in a couple of hours on the ISES website, so please check for updates there. And also in the ISES members area, as I explained in my introduction at the beginning, members, please sign in or log in to your accounts, and then you'll see all the recordings of the webinars. Please also take the discussion to our LinkedIn forum. If we missed your question or didn't have a chance to answer it in the time allocated for the webinar, post your question on the discussion forum, and we look forward to many interesting discussions there. We welcome your feedback. Please write to public.relations@ises.org with any comments or questions about this or any other ISES events, and please complete the survey, which will be launched once you leave the webinar. Well, that's all from me. Thank you so much for joining us. Thank you so much to our panelist speakers, and I wish you all an enjoyable day. Goodbye.